Hey there.
Hello.
Hi, nice to meet you all. I just wanted to troubleshoot the Zoom session. Is the video clear? Is everything smooth on your end?
Yeah, video and audio are both very clear.
Okay, cool. The only thing that I'm slightly concerned about is there is a lot of video in my presentation, and so I hope it all loads okay. If anything is an issue, feel free to interrupt me at any time.
Yes. Thank you.
Of course. It looks like we have a couple more minutes till start, should I rejoin at it'll be 11 o'clock my time in about 5 minutes?
Jesse, can you just share one presentation so we can see that we're able to screen share?
Sure, it looks like there's an audience, but I can do that. Let me pull this up.
Recording in progress.
And then, can you see this when I play it like this? It
Yes,
looks okay.
working fine. Yes.
All right, cool. So that's a preview. Let's see. All right, it looks like everything's going smoothly, right?
Yes.
Great. All right, I'll pull this down now and then I'll join again in 5 minutes.
Okay.
All right, see you then.
See you.
Hi, Ranjana and everyone at NID Assam. Can you guys just speak once so we can ensure that we hear you?
Hello, are we audible?
Yeah, perfect.
Okay.
Hello? Check, check. Can you guys hear me clearly? Check, check, check. Can you hear me now? Is it still cracking?
Back. Hi. I'm wondering if you want to give an intro, otherwise I can just get started and introduce myself.
No, we'll start, yeah.
Okay, okay.
Good evening, everyone. On behalf of the entire NID Andhra Pradesh community and the Layover team, it gives me immense pleasure to welcome you all to today's Layover session. The session is being streamed live on YouTube for our seniors and alumni, with students from NID AP and NID Jorad joining us today. After the presentation, we will be opening the floor for audience questions, so please prepare them beforehand. Layover, as you know, is a design dialogue platform created to bridge the gap between the academic and professional worlds of design. It's a space for open, reflective conversation with inspiring voices from the design community. Jessy Lu. Audio. Audible? Are you audible now? Okay. So joining us today is Jessy Lu. Jessy Lu is a textile designer and material researcher working at the intersection of textiles, computation, and sustainability. She is a graduate of the Rhode Island School of Design and is affiliated with Oxman, Mary Oxman's Research and Design Lab, where she contributes to textile craftsmanship and material innovation.
Her past professional experience includes textile and material innovation work at Apple, contributing to advanced product material development at an industrial scale. We'll hand the floor over to you now, Jessy.
Cool. Thank you so much for a beautiful introduction. And thank you for having me here. I'm really excited to speak to this audience and to get a sense of what you're interested in, and I hope I can share with you some interesting thoughts myself. So I'll go ahead and get started. Let's see. So my name is Jessy Lu. I'm a textile designer and engineer, and today I'll be sharing a little bit about my experience, first at the Rhode Island School of Design, where I got an undergraduate degree in textile design. Following that, I went into the sort of tech sector. I started working as a textile engineer, a materials engineer, a developer at Apple, and that was in the Textile Innovation Lab. So at the Textile Innovation Lab, we worked on anything near term, such as watch bands, phone cases, to the more speculative. We moved into the VR headset, and then even in health sensing and integrated electronics. And then lastly, I'll speak to my experience as the head of textile craftsmanship at Oxman, which is Neri Oxman's research spun out of the MIT Media Lab and turned into a model of research and development that can exist in the world. So to start my experience at RISD, this is a little bit of context of where I began my design thinking. And I know that this audience is sort of like a multifaceted design space. I know there are computational designers, architects, engineers, but my background is specifically in textile design, so this presentation will really, really focus on that. But I will talk about cross-pollination. So my thesis work at RISD was looking at the relationship of textiles to the past, thinking about textiles as a form of computation. A lot of the sort of like visual outputs was looking at sort of like the luminosity of the surface, sort of like eliciting screens or sort of like the allure of the screen from a more passive material. And then also that relationship of the digital to physical. So articulating in physical space through the material qualities of textiles, things that are sort of based on a digital or programmatic input. So one of the major aspects of my thesis work was working on the jacquard loom. And so this was one of the pieces that I had made. This uses a paper folding technique called Mura folding. It has these tessellating parallelograms, and so that allows the textile to expand and contract. The pattern itself is one that is used sort of, they were actually looking at this as a way of sort of compacting material for aerospace. So looking at like how you can unfold satellites, but that was the principle here is textiles that could expand or contract based on their geometry. And then as far as like the technique involved, there's a lot of sort of like maybe like the beginnings of like an engineering mindedness in the construction of these jacquards, where the pattern itself is really quite simple. The graphic is on the far left corner, and you can see that like it is just sort of like a very straightforward geometry, but then the actual material qualities are elicited from the textile using different textile techniques. So looking at the density of the textile to create areas that are more rigid, channels that are more compliant, that enable the material to sort of like fold onto itself. This was another version. Instead of using that sort of like parallelogram Mura pattern, this is just using sort of like more vertical pleats. So here you are beginning to see that sort of like relationship in textiles, the 2D manifesting in the 3D space, and then really, really just like committing to the integrity of the physical material itself. And then in addition to industrial weaving, I was also doing industrial knitting. So these are samples that I made on the Stoll industrial knitting machine that RISD also had. And then here, I think the exploration of material qualities is also evident. So you can see on the far left, this was looking at this diamond pattern and applying different knit techniques to the face and the back such that it would sort of like pleat or like self-pleat. And so these are like all very dynamic. Same here, you're looking at sort of like this curling behavior that's inherent to knitting, eliciting like very different both material and aesthetic qualities on the face and the back of the textile. And then even in like this far right, thinking about like simple jacquard pattern elements, like you're using these sort of like grids that are rigidly logical. When you look at them on a computer screen, they're really just like pixels, right? They're like X, Y, you can see them very rigidly, but then in the textile form, you can see, oh, you're beginning to elicit these visual effects that look like fluid dynamics, and that's based on the mechanics of the yarn. So you can see that in this one. And then I talk a lot about weaving and knitting, but I would say that all of these industrial technologies, they like really play a significant role in industry. So I think, I mean, towards the end, we can talk about the way that education and the education that like everyone here has had moves you into the world. I would say that those projects really were like a very significant underpinning to my time at Apple. Just at a high level, I'm going to talk a little bit about textile technologies. Industrial technologies, there's woven textiles, there's knitted textiles, there's also non-woven, which might be felting or melt blowing, electrospinning, like leather is an example of a non-woven. But even within this, you can become extremely specialized. So I mentioned the Rizzi Jacquard loom. This is one form of industrial technology. But at a high level, like these are what industrial weaving machines look like. And we have these at Apple. So these ones here are weaving, they're like industrial jacquard looms. Well, actually, the one on the left is a Dobby loom, but this is a narrow weaving industrial machine. And then on the right, this is sort of like a cutting edge jacquard weaving loom with a cream, like a belt take up, very, very complex. And then in the upper right corner, you can see that's the mechanism by which the fabric is made. So in weaving, you have the creation of a shed, which is sort of this like aperture in the threads, and that's how the fabric formation gets made. You also have this is flatbed knitting. So flatbed knitting is, it's also called well, this is actually weft knitting, but the material is being delivered on the horizontal. And on the far left, this is a small diameter circular knitting machine. This makes socks. The needle bed is circular. In the middle, you have a large diameter circular knitting machine, and this makes yardage. So you can imagine like t-shirt fabrics. This often is cut and sew. And then on the far right, this is a flatbed knitting machine. So the needle bed is flat instead of being like a cylindrical bed making material on the round. The needle bed is flat, and you can make 3D shapes this way. In the upper right hand corner, you can see like the needle actuation that forms the fabric. And then lastly, there's warp knitting. Warp knitting on the far left, narrow warp knitting on the right, very wide. And the mechanism also you can see is sort of like these guide bars and needle actuations. And then so I cover all of that because I think that those industrial technologies, they really, really play an important role in the material qualities of the textiles themselves. So this is a project that actually came out quite recently. This is a tech woven case at Apple. And this seems really trivial, but this was actually like a very important project because Apple at this point in time had been primarily using leather in their soft goods to make these cases that connoted luxury. And leather is not such a sustainable material. It is like natural and biodegradable, but it does have a carbon footprint in terms of just like using leather that comes from cows. So the question here is like, how can you create a sustainable alternative? And with textiles, textiles really can answer that question because in this case, what we were trying to do is create a material that could take recyclable material and then maybe itself be recycled. And in this case, it's a post-consumer recycled polyester that creates a woven textile. And when you hear those words, you don't necessarily think, oh, that's going to be like an object of luxury. And so something that was really, really important about this project is how do you create the sensation of like luxury, of like a premium material that can compete with leather, but still like maintain those sustainability ideals. And so in this case, we developed a woven textile that was extremely, extremely fine. You can see on the right here, this is 490x magnification, and then that's a strand of hair. And so a hair is maybe like 72 microns in diameter, like a single hair off your head. And in this case, each of those filaments are like 6 microns in diameter. Like each of those like tiny filaments in that bundle of yarn is 6 microns in diameter. And so because the yarn itself is so small, when you touch it, it has this sort of like suede like feeling. And that's how like from an engineering and a textile design standpoint, you meet the challenge of like how do you create like a textile that feels premium and luxurious. And this really is only possible with industrial technology. It's like this is sort of like what it looks like when you're sort of like pushing any given technology to its sort of like meaningful potential. In general, in textiles, there's like a lot that goes into it. The yarn itself is like very, very important. So this is a slide that I had made just sort of like walking through the textile production process. You start with the yarn, there are all these like secondary steps, and then there's the actual textile fabrication itself, and then the finishing. Within yarn, the one on the far left, I would say, is like most similar to what was used in the tech woven case. This is sort of like areas in the space of like materials engineering, materials science, where you're looking at like, I mean, weaving is like a very aggressive process. Like you have this like shed creation that I had sort of shown earlier, which is like, like there's a lot of like tension on the yarn, and then there's actually like the weft insertion and it gets pushed back. So when you think about weaving with something like 6 microns in diameter, the question is like, oh, how do you weave with it such that it doesn't break? And so there are all sorts of material science solutions that sort of how do you like weave with a thicker yarn and then it breaks into smaller yarn so that you get that sort of like luxurious hand feel. This is one way of doing it. There are a lot of other ways. There's sort of like co-extrusion techniques. On the far right, you can see this is an example of co-extrusion. So you have like two materials that are extruded side by side, and then because of their different material properties, they in this case they turn helical. Their differential shrink rate makes the yarn curl, and then it creates sort of like a mechanical elastic. But you can also use this to create that suede-like texture using two different materials like polyester and nylon. And when you like subject them to agitation and chemical processes, then they sort of like break apart and become smaller, and you get that like luxurious hand feel. I always think that this is like a very fun part of textile development, but like each of those 6 micron filaments can themselves not just be circular, they can have all of these other material properties. Like these are all like microscopic images of what a cross section can be, and all of these different cross sections result in different effects. So those effects can be like, oh, it might be more able to retain like a garment that keeps you warmer because the fiber itself is hollow, and because of that, air is a poor conductor of heat. It prevents heat from sort of like exiting the system. And so like polar bears have that. This is sort of like looking at like biomimicry, which is, well, a polar bear stays warm because its fur is composed of these hollow fibers. How do we mimic that in yarn production? And so these are also all techniques that exist on the industrial scale. And then all of that sort of like leads into some of the work then. In addition to the case, one of my first projects was the Apple AirPod Max, which has many different textile components on it. This was also sort of like a challenge looking at headphones at the time, all being sort of composed of leather. How do we make this out of a more sustainable material and out of something that just feels like fresher and newer as far as the design language? So I worked a lot on this project. This is my first project. But the driver textile is a warp knit, canopy textile is a warp knit, the ear cup textile is a circular weft knit. And then the Apple Vision Pro is also another product that heavily leverages textiles. So the light seal, which is the part that contacts the face, that needs textile. It uses textile and foam because it's something that just like contacts the skin. I would say that like in general, as you move towards products that contact the skin, like here, this is like a phone and it's made out of like glass and aluminum, and it's like basically like a brick you carry in your pocket. Things that you wear on your body, they are textile for a reason. They're like soft, conformable, they can drape. And so this light seal contacting the face uses textile components. My team at Soft Goods, composed of materials engineers, worked on this. And then one component that really heavily leveraged flat knitting, which is an area that I focused on, was the band that keeps it on your head. And you can see here, this is actually like quite a complex knit. There are all these like engineered zones. This is all knit as one piece. So all of this sort of like folding and unfolding, contracting, like sort of like relaxation, and this inlay of the cord, how you finish the edge. And in the upper right hand corner, like more complex geometry, so you're making like turns in the textiles. All of that was like you needed to program and prototype that and test it for fit. And like you can see here that even on this scale, all of those ideas of like the mechanics of the textiles, like the mechanics of materials that exhibit dynamic qualities, which I was exploring in my undergraduate research, it like persists a lot and persists very much so in the textile space. So that was my time at Apple. I spent a good amount of time there. I think 7 years in two different roles. And then that led me to my time at Oxman. And Oxman is Neri Oxman's research spun out of the MIT Media Lab. Following her time at MIT, she started building a larger space in Manhattan. And so some photos here. This is a picture of what we call the robotics cell, and I'll get more into details on this later, but this is sort of like a platform for fabrication, really, like any sort of physical fabrication that we would do, any sort of product that we might speculate on had the idea that there was this vertical integration of all of the steps being housed under one roof. This is a robotics cell, and this is the wet lab. So in addition to the physical fabrication piece, we also had a lot of research, fundamental research happening in biology, synthetic biology, microbiology, and chemistry. And that fundamental research was all sort of feeding into the way that we conceptualize design. One of the major projects that I worked on was called O0. This is a bio-based biodegradable shoe. The value proposition here is that textile waste is a big problem. A lot of shoes end up in landfill. About 22 billion pairs of shoes every year end up in landfill. Shoes themselves are a constituent of many different materials and many different parts. Maybe 40 to 50 different materials go into that stack up. So you can see on the right, like all of these materials, not only are they petroleum based, but they're glued together. So even if any one of these components were recyclable, the fact that they're held together by adhesive means that they can't be separated. And so that contributes to a textile waste problem, a consumer waste problem. And so the idea of O0 was that that could be obviated by design and through design and through like a true commitment to nature centricity. This was a slide that I worked on with my colleagues, but this one kind of describes like the overarching concept of O0, which started from the biology itself. Like, how can you look at biopolymers? How can you engineer biopolymers? How can you leverage nature to create materials that belong in our world and then also degrade in our world? And so that fundamental science leading into forms of fabrication, which included textiles and included robotics. And then there's a heavy component of computational design. I'll speak a little bit about the computational design and fabrication piece. This is not my area of expertise, but this was a big part of the project, which was the computational design was using tools to create a design space that potentially is wider than what exists today, especially in the shoemaking world. Instead of the sort of like traditional idea of you have a standard stack up, the upper, the outsole, midsole, laces, could you expand the design space such that using computational tools generate many different sort of expressions of design and then also take into account feedback maybe from like the biomechanics of the foot or like person to person variation in bone structure and musculature? Could all of those be accounted for in the design of the shoe itself? And then in the fabrication piece, could all of those shoes be made one-off, custom to the foot without the need of making excess where you are keeping inventory in all of these sizes, like women's 7, men's 10? What if you could just make shoes that met the needs of the consumers as it arose? So that was the conceit for the project itself. And then the platform for doing it was one that I think Oxman very much establishes in the physical architecture of this space. So this is a robotic cell. Here, this is the robotic fabrication that I just alluded to. The UR robot on the left is where we started, and then we were also in the business of building our own robot. So this is one that my colleague Florian worked on. This was a way of doing the shoe production in a highly lean footprint. And the idea is like you could have a factory like modular with all of these individual robots producing shoes with their computational input. The idea also being that this could be in a store. This is the equipment that I primarily worked on. This is the Stoll flatbed knitting machine. And then on the left, it's like an AgTex winding unit. And then there's also some fiber making equipment. I think the next slide. So this is the fiber making equipment. And I would say that the biggest lift on the project on my end was in the fiber. So I'm going to talk a bit about that. We had a fiber line, and this is like how fiber making works. Typically in any R&D facility, you're not starting with making the fiber, but at Oxman, I think we challenged ourselves to say like, can we like synthesize the pellets? Can we turn those pellets into yarn? And so that's what we're doing here. This was in our lab. We were making all of this yarn. It was like making yarn is a really huge challenge because you're taking this material and you're drawing it out. We were never at sort of like 6 microns in diameter per filament, but we were hitting like 30 microns in diameter. It's really, really thin for, you're making like tens of thousands of meters of material, like kilometers of material so that you can like actually make textile with it. And so it's like really just like a testament to the material science piece that you're able to take. In this case, it's a biopolymer, and you're able to turn it into yarn. And then the biopolymer itself, this is where even further upstream of the yarn production, we were using a class of biopolymers called polyhydroxyalkanoates. So this is a material that is very interesting because a biopolymer can be synthesized by bacteria. So on the far left, you can see bacteria, and these little granules inside the bacteria are the biopolymer being synthesized. The bacteria basically uses a sort of like a carbon storage mechanism. They use it like the way that humans store fat in order to like have energy. But in this case, it produces a material that is very useful to us. The material properties are similar to polyester. And so when you extract it from the bacteria, you can do things like make yarn with it. You can 3D print with it. So on the right, you can see a knitted textile that I worked on, which is made from this material. And then for that project, O0, I was the primary researcher on the first 100% PHA knitted sock. And then as the yarn production and the sort of the material science polymer process relationships were sort of being developed, we were able to make more and more complex knits. And so between the top, where you can see like that sort of like very organic quality was based on our inability to to like successfully extrude like stable, consistent yarn, to the bottom where like actually the visual complexity is based on like us being able to control the design space because the yarn was stable. And so then I'm able to like program in complex designs. That was like a very meaningful development in the material science space. And then those were the bases that we were able to 3D print with the same material chemistry. So on the right is a 3D printed pattern of the same, using the same biopolymer polyhydroxyalkanoates. And this is a video of the shoe itself biodegrading in an enzymatic rich solution. You can see here that like really the textile goes away the fastest, and then what you have is like the sort of like the degradation of the print itself, which has a lot more volume. Then this is the knit here. You can see that this is like the biodegradation in process. The loops are sort of very clearly visualized on the left. This is like scanning electron microscopy imagery. And then like as it's degrading, it's beginning to fall apart. And textiles is a really great platform for this because compared to 3D printing, textile just has so much more available surface area than the degradation, just like it is really effective in this form factor. And so this is one area in which I think textiles was a pillar of fabrication for Oxman ideals. And those ideals in this case was the idea of like polymer chemistry, material science, and fabrication coming together to articulate a design expression, which is a textile, a shoe. And then the next project that I'll share with you is a specific project that I think also embodies those ideals, but with a slightly different research focus, and that is in the idea of bacterial pigmentation. So this was still using this shoe as a sort of platform, but all of the designs you'd seen prior was sort of like without color. And so one really meaningful research project that came out of that sort of like iterative process with the idea of bacterial pigmentation. So my colleague, Marcus Walker, incredibly talented, he's a synthetic biologist, and one of his projects was looking at how can you engineer bacteria to create complex macromolecules. In this case, those macromolecules are color, they're pigment, as part of their gene expression. So when the bacteria grow, can they produce color? And so here you can see he's working with two different inducers and a range of different textile fibers. Like on here, there's like cotton, there's silk, there's wool, there's the PHA fiber, actually the polyhydroxyalkanoate based fiber that we made. There's synthetics, nylons. And so he here is just doing an assay of like, oh, what or he's doing a study where he's putting these fibers onto these agar plates and seeing how the color is expressed. And then with relevance to the shoe project, the idea is like when you have a material that's made, in this case, it's the knitted material, it's the sock design. When you have this material that is like coated in this bacteria that can produce color, can you meaningfully produce color? And so this was one of the first trials that he did. The textile starts off white, and then in this case, it's producing the color melanin, which is it's brown. Melanin is present in your skin, in your hair. It's present in mushrooms, in bird feathers, and it produces this sort of like deep, rich, earthy tone. This is a video of a self-pigmenting sock, and so in this case, the color expression is indigo and indie ruben. And so here you see the bacteria is like producing the color, it's producing it onto the material itself. This is what the final sock looks like. And so I would say that like both of these projects embody a lot of that Oxman magic. I would say that like as far as the idea of how research and development can happen in sort of a multidisciplinary space, that project, I think, very much embodies it. Oxman is working on several different projects right now. But I would say that that vertical integration of knitting, of robotics, of synthetic biology, microbiology, chemistry, material science, it like all really comes together to create this like transformational quality of design expression. And I think that that design expression can move us towards a better world. So to move us towards a world of like to interrogate how can things be built and how can they be built better. And I think that's all I have. That's 30 minutes.
Thank you so much, Jessy. That was such an invigorating session and lovely presentation, by the way. You've had such a vast and expansive career. Thank you so much for sharing that with us today.
Yeah, of course.
There were so many things that we related to. Like, I think each one of us has gone through the phase of making tessellations for foundation. And I remember one of my friends in textiles telling me that one of their initial assignments was to spin like 3 kilometers of yarn, and then the thread would keep breaking, and the whole process of that. While that is there, at the same time, there were so many things that were new to us and a lot of exposure. So we would love to know a lot more. We have so many questions.
Yeah, of course. Feel free to ask.
We will open the floor to the audience soon. They can think about their questions. Until then, I had something to ask. Throughout your thesis project, you had worked on folding mechanisms for textiles, right? Do you think there is an edge to textiles when you mix tech and the traditional textiles on it? Because where we come from, there's a lot of focus on the traditional way of making textiles. So, what is your take on that?
The question is between traditional textiles and or more industrial textiles, is there an edge to doing it? Yeah, that's interesting. I mean, I think that both really have a lot of value. One thing that I think is really important is a lot of my skills are indexed on industrial technologies, but I do think that everything comes from like a foundational craft lineage. So anything that's made by a machine had to first have been made by hand. And I think an intuition for that material is still really, really necessary, even if you're having a machine do it. So, for example, like traditional techniques, like even when you're hand weaving, hand knitting, hand spinning, like hand embroidering, you're using these sensors in your fingers, and these are like the most sophisticated sensors we have in the world. The way that you can like feel something, the way that it retracts underneath your fingertips, that really can't be mimicked by technology as it stands today. So I think that there is like fundamental knowledge that's in those sort of craft traditions and traditional ways of make that are very, very valuable. And I think it would be a loss to sort of look only to industrial technologies and forsake those. One thing that I think industrial technologies do really well is they are able to make material very quickly. Whether that is a virtue or liability, I think is maybe a more abstract question because the ability to produce material very fast is something that like industrial looms, industrial knitting machines have been developed to do. And that I do think contributes a lot to um, like a culture and an economy of fast fashion. I think that there are definitely like arguments to be had about the detrimental impacts of that. But I do also think that some of those industrial technologies have created innovations. A lot of like aramid textiles, for example, ones that are used in aerospace, ones that are used for any sort of like high strength geotextiles. Like a lot of those do need to be made through industrial technologies just because, like, for example, in medical applications, the homogeneity, if you have like a textile that's being like embedded in a bifurcated system, then you don't want any sort of like blemishes or artifacts that might come from like a handmade process. So the homogeneity, the consistency, the repeatability, the ability to work with sort of like very high strength fibers, I do think there are very niche applications that industrial technologies could pose an edge in.
Thank you, Jesse. That was like such an insightful answer. Like, I would like to ask you another question. So when we talk about textile, and it's like different places has a very rooted culturally influenced textile. So lastly, like we had also talked about your project in Taiwan, which was like research based, and now you're working at Oxman, where it's textile that is ahead in future. So, is there anything that is connecting those culturally rich textile that is being continued since generations and now working on something that is very future centric? So, how both are inspired and how things are different and similar in those?
Yeah, definitely. I wasn't sure if I should talk about the research in Taiwan when I was putting together the presentation because there's that 1 year gap between when I was at Apple and when I started working at Oxman, where I would say in some ways Apple is very like it's a little bit like outside of culture. I would say a lot of the design aesthetics of Apple was driven by sort of like these ideas of like universalism or I mean definitely informed by a more European tradition of sort of like very clean, like, like Swiss design. But the rhetoric was always sort of about this like more universal design of like, oh, how can these like radii on the corner, how can these materials be like palatable to like a global audience? And so much of that was just being driven by like technology, the technology for making things. So tooling, different sorts of like sensors for measuring things. All of that I think was like very much moving towards something that was like more general, more global, more universal, and less specific. And I think culture is very specific. And so after I left Apple, I'd gone to Taiwan to do a research project, and that I think was almost the polar opposite, where instead of looking at like what can like machines and technology do, I was really just committed to investigating craft tradition and looking at Taiwanese craft tradition in particular. So I'd spent that year doing a research project where I was looking at the history of various crafts, which included indigo dyeing, bamboo, rush weaving, which is a form of grass, all of these different ways of making things in through traditional methods that were very much based on like the specificity of Taiwan as a locale. So thinking about how a lot of those materials, whether it's bamboo or grass or indigo, those all came from plants that were like native or naturalized to Taiwan. And so like the visual output and the material output is something that is like so unique to that place and really like can only have been made in that place. I think there's something like very, very special in that. And I think that even in thinking about the way that that project also evolved was thinking about like the visual landscape of Taiwan, like especially in urban environments, like you can see that there is also this like movement into new materials. There, like Taiwan has plastic production, and they would that's a big form of industry for them. They have semiconductors, and so thinking about like what is like the culture and material landscape as you like move through time and move towards the future and like what is preserved and maintained and then what sort of like manifests in sort of even just like the psyche of the material. And so I think that it's interesting because then coming to Oxman, I would say that was almost like the perfect hybrid of both of those prior experiences. So the more technology focused experience at Apple with a heavy emphasis on engineering to bringing in that sort of like culture and craft tradition. Because I think that as you move towards the future, you don't necessarily have to move into a world where it's like petroleum based plastics or like high performance textiles. I think that there is a really profound question of like, how do we acknowledge who we are and like the planet that we live on in terms of how we do design without thinking like, okay, let's just go back to homesteading. Like everything that I make is going to be something I had to make by hand or like I had to sew it and it had to be like I grew the grass that like became the basket. I don't think that that's necessarily an answer as like the population grows, as we sort of like develop more tools and technology. But I do think that we owe it to ourselves to say like, how do we like maintain our humanity and how do we like consider materials with integrity, consider like the the life that exists in the material and our relationship to it in terms of like building things that we use and in terms of the life that they have even after they become less useful to us. So whether they are recycled or composted or biodegrade. Um, one of the one of the sort of catchphrases of O0 was bacteria to bacteria, which was the idea that the bacteria would produce the biopolymer, the polyhydroxyalkanoid, they would make it, and then would be like transformed into all of these states, whether it be yarn or 3D printing or melt blowing. And then like as it degraded, you could put it in the soil and the bacteria in the soil would then eat it as food. Because it was a carbon source. The same carbon source that existed in its like creation also exists for the bacteria in the soil. And so I think that yeah, I mean, I think that that's a very like human culture. And I think that anytime you're designing, the perspective and the lens of the designer brings along with it the cultural heritage of the things that are specific and local to you. And then there is something very cultural about just like fundamentally being human and how we sort of like make things for us, but then are also for each other. And yeah.
Same topic. When we think about sustainability, there are two approaches. One would be taking or making an object or a product that sustains through time. It's durable and it doesn't like perish early. But another aspect would be what you have done with your the shoe, the biodegradable shoe, to make something that is completely compostable. So I think is harder to make and harder to achieve.
Um, I think really, really complicated question. I'm sure that you all have heard like in the space of like sustainable materials, there's recyclable, there's compostable, there's biodegradable. They all have like very specific definitions for what constitutes each. So in the case of recyclability, that might be in the world of like recycled polyesters or papers or aluminium. This is something where it's like the input material is based on some kind of chemistry. It can break apart and then be reconstituted, and you don't get too much loss from the reconstituting of the original material. Compostability and biodegradability, there are some differences because compostable materials usually require some infrastructure in order to break it apart. And so some materials are more readily, it would be called home compostable, where you could like maybe put it in, if you had like a compost pile that was sort of like high heat, high humidity, bacteria rich, then it would degrade there. But usually a lot of bioplastics that you see, like bioplastic, like forks and knives, those ones require industrial composting facilities where you have like a big facility that brings the material to like high heat, high humidity, and like there's like a whole industrial setup because that temperature and those conditions are higher than might like naturally occur in your environment. And then biodegradation is something that I think is much harder to achieve, but is the idea that like you can use these ambient conditions like the soil in your backyard, the soil in a garden, maybe lake water or salt water in the ocean, and in those conditions, a material could degrade. And I do feel like if you're in that sort of like compostable, like biodegradable space, that's kind of the North Star because I mean, even if you think about a scenario in which like you have a fishing net and it goes like you accidentally lose it, it goes into the ocean. If it could biodegrade, then it would degrade in the ocean, but it wouldn't necessarily cause harm. The same with like a shoe in the soil. It's like, oh, you could just bury it in the backyard and it would just go away. It is sort of like this question of like microplastics is usually microplastic means that when it breaks down, it like does not go away. But in the case of a biopolymer, Or in the case of like wool or cotton or silk, if it goes into the soil, it is breaking down into smaller and smaller pieces, but the main thing is that it does go away. So I do think that biodegradability in some ways is like it has like a lot of shining virtues because it doesn't require the same infrastructure that composting needs or recycling needs. Like in both of those cases, you take the material, you bring it to a facility, and it gets processed there. But if you don't have the facility can be expensive to make, expensive to build, or if it doesn't make it there, like if you like lose it, if it like, you accidentally put it in trash instead of composting, if it doesn't make it there, then it's basically the same as trash. So like that I do think is something that biodegradation fixes is or resolves is to say that like even if it does end up in the world, it's not going to cause harm. And then the last thing I'll say is like one ideal of that uh of the shoe project was like sure a sock could be made from like cotton or wool or silk and it would be bio-based, like it came from a plant or a living source. It could biodegrade, like you'll put it in the soil and it like, will go away. It might even like add to the soil microbiome. But it was actually very important for us to use a biopolymer in particular, something that exhibited thermoplastic properties. So you could like melt it down and you could like draw it out into all of these forms. The fact that it was thermoplastic means that you can like do lots of things with it. You can 3D print with it, you can knit with it, you can weave with it, you can electrospin with it. Like that alone from a design standpoint is really interesting. But there was this other really, really interesting idea, which was that because it's thermoplastic, like at a certain point, it's like melted. It's like in a liquid state. And at that point, you can put in additives, and those additives could be something like nitrogen, something that soil actually needs in order to give nutrients to plants. And so if you had something like a biopolymer that the matrix was doped with something like nitrogen, it would have it in the shoe, but then as it biodegraded, not only would it be potentially inert to the environment, but could you actively be adding nutrients to the soil so that when it degraded, it was actually promoting plant growth? And so that I think is like it's interesting to answer your question about like, oh, like, is there sort of like one that's better, one that's worse? I would say that like that's a really interesting value proposition, which is like as far as sustainability is concerned, not just like how do you not do harm, like how do you like, oh, you can recycle it, you can compost it. Those are all like harm mitigation strategies. But like, is there a world in which when you design, you can actually do good? Like because you made the shoe, it has nitrogen in it, it's actually helping plants grow. Like, I think that that's a really interesting way of thinking about design. And like, I think it's like a very beautiful way to think about design. And then I think on the other end of it, it's just like really hard to do. Like, there's a reason why you have like composting and biodegrading or composting and recycling is just because it's a little bit easier. Like the things that you shoot for in terms of your ideals, like they're really hard to implement. And that's why we're trying. But yeah, you have to have steps along the way.
Good to know. And I think we relate to it a bit because all of our projects, they were somewhere connect to all of it. But yeah, that was so nice to know from you. I would like to open the floor to the audience now, if anyone has any questions.
Everyone already
Am I audible? Yeah, okay. So, what was the like biggest hurdle faced while scaling up the PHA-based products from lab prototype to products like zero degree shoe for a mass production?
Yeah, there's so many problems. One thing I'll say is I don't think I wouldn't say that product ever made it to mass production. It depends on like what you call scaling, but I would say that the PHA shoe was something that was only established really as like a conceptual foundation, and we only ever made like maybe maybe like a few hundred at most. But I think that it does create a very interesting question around process stabilization. I would say, I mean, in the world of hardware engineering, to scale anything is just extremely, extremely difficult. And like even some of those earlier examples where I was talking about like, virgin PET to recycled PET, like even that transition is just like it's really like there are problems. And so there are problems that arise that you solve through engineering. And so developing anything from the ground up is just very like you encounter like a whole slew of things that need to be solved. So with the PHA in particular, like where do I even start? Like one thing was with polyhydroxyalkanoates, like there are two routes to making it. There's like biologically produced and chemically produced. And so you can produce it in a lab, but we were very invested in doing it through bacteria, through using like a biological form of production. And in doing so, you have impurities in material. And those impurities can cause process instability. So things like batch to batch variation would mean like either the yarn is made or it isn't made. It's like the impurity can cause it to break as you're trying to draw it out. Um, and on the yarn side, like not only was the sort of like impurities an issue, but it was like that particular biopolymer, it has like a very narrow processing window. So with something like polyester or polypropylene, the processing window, which is like the upper and lower bound of the temperature it can be at, it's pretty big. So you can like have some flux in the process where it's like the machine gets hotter, it gets colder, or like maybe that day it's more humid or less humid. Like you're still probably going to be able to draw a yarn that is consistent to the degree that it can be viable in a product. But with this class of polymer chemistry in particular, that processing window is really narrow, which means that like the conditions really have to be like very perfect and stable in order for you to be like successfully either like drawing material or printing with it or melt blowing with it. It just like requires like a much higher degree of finesse and a much higher like the process stability has to just be at a certain bar in order for you to be like reliably making parts. Um, I think like another thing that came up was just sort of like the functional performance of polyhydroxyalkanoates, PHAs. Um, a lot of materials, like when you think about a shoe, a lot of it is made from like polyurethane, which is something that is like very much like not biodegradable, but it's a very, very good material. It's like bouncy, it's elastic. That's why your shoe sole can be made from it. Polyurethane is like very easy to work with, but and then once you work with it, it exhibits these like great material properties that last for a long time. Like you can have a pair of shoes for like 2 years, 10 years. Um, PHAs were always something that like their material properties just aren't as wide, like the way that you can flex it, the way that you can twist it and bend it. So that's, I think, where the design comes in is like there are lots of shoes, like they're like stilettos and high heels and like clogs where maybe it's not as like stretchy or bouncy or elastic or compressible, but you can get away with it because of the geometry of the thing, the way that it conforms to your foot. And so that was also an area that we found with PHAs was because it wasn't so like elastic in its properties. We would always have to like compensate for it in the actual like design of the tool path or the design of the shoe itself in order for it to be comfortable but also like durable. So yeah, I would say a lot of things came up, and then even just as far as like the robot that we made was one that was like it was designed to scale, but still even like the knitting equipment is one that like you can go to a factory. There are like many different factories that have hundreds of these machines that are already set up for the production of things, such as like shoes or shoe uppers, sweaters, mittens, all sorts of things. But like if you're designing your own technology, then like you also have to look at scaling that up. Like you can't go somewhere and they're already going to have 100 of them. You have to actually build out that facility and that infrastructure. So like all of those questions came up. Yeah, I mean, I could go on about like all of the challenges that arose.
Yeah, we had one more question.
I just wanted to know that I found that luminous textiles are a very interesting area that you were talking about. So generally it can be only seen in projects or maybe in some luxury sections, but how it can be also introduced into the electronics or how it can be introduced to the mass production, I would like you to expand a little more on it.
Mm-hmm. Yeah. When you say electronics, do you mean like integrated electronics, like in wearables and?
Yeah, of course, like when you're talking about the earbuds or maybe the phone cases. So
I see.
textile, also in the medical sectors, if you're talking
Yeah,
about.
definitely. I mean, I think it's a great question. I think that textiles, as someone who has been working as a textile designer and textile engineer for a long time, I do think that it's a material that um, is really underutilized in all of these spaces. Like something that I used to always say was like, textiles is a solid material that exhibits fluid dynamics. It's like a solid that acts like a liquid. And it's because it's like, it's so drapable and conformable. That's what gives it a lot of like authority in all of these spaces. And so you see it the most in apparel, maybe in the luxury sector. You see it in interiors, like in curtains, upholstery. But I do think that the potential for textiles is like much broader than that. And medical textiles, I think, is one space where textiles are like very, very interesting and hold a lot of promise. I'll list out a few more, but then I'll talk about medical textiles in particular. I think textiles also are often used in like aramids, like in the performance space. So it can be like aerospace. For example, carbon fiber structures are often made with textile techniques, and that can be like anything from like carbon fiber, like bike frames and surfboards, to wind turbines, like the sort of like long blades being made out of like a braided carbon fiber. Aerospace applications, automotive applications, like wheels, headliners, cars, like frames, things like that. Geotextiles is another one where it's sort of like textiles for managing of landscape, sort of like if you're using it for agriculture, if you're using it for like siding for like rock faces, for architectural applications. There are textiles that are used for like dampening sound in spaces, for refracting light in spaces, different like scrims and things like that that are like dynamic. But I would say that like medical textiles is probably one of the more interesting applications of textiles to me, and like really like in all of these examples, you choose textiles because it is the thing that needs textiles. Like the fact that it's conformable, drapable, can create these like three-dimensional curves. Like even the wind turbines, like the fact that it's a braid and you can like cinch it down, that's really important for the creation of that geometry. It's also very strong. But medical textiles, the reason why I bring it up is because like the way that it exists outside the body as far as clothes is also what like enables it to, I think, meaningfully be inside the body. So there are medical textiles that are outside the body, like compression garments, like sleeves and things of that sort. But then I do think a lot of really interesting research is happening with like tissue engineering and textile scaffolding. So the idea that you can like weave and knit these like bifurcated structures. So if you were going to like put a stint inside your body for like any sort of like operation or procedure, what you can do is like you can have that textile be a degradable textile, non-cytotoxic. So when it degrades, it won't cause harm. And then you can like coat it with an enzyme that promotes tissue growth. And then as it's degrading in your body, the tissue is also forming around it. And so the tissue is given a scaffolding to regenerate. And so I think that that's something that like uniquely textiles can do. And so I think that there's really interesting research being done there now. There's like other sorts of like textiles as sort of filters for like maybe like diabetes applications, like diffusion, like slow release diffusion of different sort of treatments. Um, yeah, I think that the space there is like really quite large. And then you had mentioned electronics as well. I think integration of electronics and like harder components into textiles is always interesting. Like that was something that came up a bit at Apple, and something that did become a product pretty early on was like a replacement for a confab material in an iPad unit, which was instead of using like a more rigid uh like like laminate layer, it was taking a woven textile and then like weaving in these wire traces. Like the wires themselves can be very, very small. Like you think about wire and you maybe like go to the hardware store and you have something that's like 8 millimeters thick. No, this is like 30 micron wire, and you can like weave that in, and it ends up being like very flexible, but also it actually ends up being a more economical alternative too, because you're using less conductive material. Like you can place that wire in the places that you need along the warp of the weft. And you can be really selective about it, so you can use less metal. So that's one example. But then I think that like if you were gonna speculate on a future of wearables where you're like integrating like sensors like EKG sensors, EEG sensors, EOG, and like you would wear it on your body, you would have those sensors and sort of like circuitry within the textile, maybe some way of like energy storage, whether it's a battery or something like that. Like they're all really, really interesting problems. I think people are actively working on it. People are actively working on like, oh, how can you like draw a fiber battery? And I think that like I do think that that's where like a lot of the cutting edge and textile research is happening. I think that they're very hard technical engineering problems to solve. I think more people should be like thinking about those things and thinking about like what kind of futures working on those technologies can bring about. So yeah, lots of interesting spaces even outside of fashion.
Yeah. Thank you, Jessy. Unfortunately, we will have to leave right now. Our studios are closing.
Oh, thanks. I know it's late on your end. I appreciate you listening to me and spending time with me.
The session was really insightful. Thank you, NID AP, for inviting us.
Thank you.
Thank you. Bye bye.
While they left, we still have 20 minutes.
Sorry, I wanted to confirm, did you have any other questions or is the session over?
We have one question from the audience.
I wasn't sure. I was like, oh, maybe just that one group needed to leave. So then I rejoined.
Yeah.
Okay.
We still have 20 minutes, so
Oh,
we can take
perfect.
a few
Okay,
more questions.
I'm free and available. So
Yeah.
Am I audible?
yeah.
I wanted to ask how you ended up at this intersection between textile and technology while at RISD. So was it a first thing that you were interested in, or did it come from somewhere?
Yeah, when I was in school, I never thought, oh, that's the thing I'm gonna end up in. I think that, so I graduated back in 2015, and I think all of this was very, very new. So I think even conceptualizing it at the time was never something that was like so obvious. And maybe it's different for the time that you're in, which is to say, like, I do think it's like more at the forefront of your imagination. So you can say, like, oh, I want to be at the intersection of design and technology. I think that that's like such a great place to be. But for me, I would say how I ended up there was because I think I was always interested in like textile mechanics. And like you see that in some of the things that I was doing in school is like, oh, how do you think about like the mechanisms that exist that are latent within the material? So like the reason why a knit curls like that is because like the topology of the loop structure is inherently asymmetrical. Like when you're making a knitted loop and like even when you're hand knitting, like the geometry of that formation is not symmetric, but the geometry of a formation of a weave is symmetric. So it's like those things I felt like I had always been interested in. And I do think that that way of thinking ends up being really, really important when you're doing anything that approaches like hardware engineering and technology, because there is like a certain degree of like needing to understand how something works on a fundamental level before you can do anything that like pushes the boundaries of it. So it's like if you're dealing with fundamental questions of like material science, and you really need to understand like mechanistically what's happening. So I think it's like that way of thinking that sort of like allows you to sort of even interface with someone who is doing work in an engineering. Like if they're an electrical engineer, if you can just talk about textiles in a way that demonstrates like, oh, like this is an opportunity for where you can insert a wire, and I know that because I know textiles, then like that sort of thinking gets you there. Like that's sort of also like what gives you availability, not just to like technology, but also like I feel that that's the sort of like bi-directional exchange that I have with like biologists and chemists, is to say like, oh, like this thing that exhibits elastic properties, and then like my colleague can say like, oh, this is just like how protein structures like fold and unfold is like a same sort of like elastic behavior. So, I don't think that that intersection was ever like the goal that I had in mind, but just like the way that you think unfolds that path.
I think we have one more question.
Mm-hmm.
You just talked about your colleagues telling you more about the scientific aspect of it. So we were really curious to know how these cross-functional teams at Oxman work. How are the briefs given out? How does the collaboration happen between so many different fields?
Mm-hmm. Yeah, it's interesting. This is, I think, like gets into a question of like how ideas come to be. Oxman is always conceptualized as being sort of like the Bell Labs of biodesign. And so Bell Labs was an arm of AT&T, where they developed like all of these new technologies, including like a GPS and like all of these sort of like novel things, like this innovation studio. And so I think that one of the things that like Oxman was conceptualized as was like we'll bring together like pillars of disciplines, people who are really, really good in their respective fields, and that cross-pollination alone will create very dynamic um, innovation, invention, new technologies. And I do think that a lot of these ideas, that is how they came up, was just like, oh, what are like the potential ways that like this material can be used? What are the avenues that like meet a lot of the principles of nature-centric design? And those principles, I think there is sort of like the way that you like measure like the sustainability, or like the the nature centricity of it, but then there's also like the material science, like the material itself, the fabrication method, the computational design space. Like I think that when you're thinking about like what is a good idea, it needs to hit a note in all of those categories in order for it to feel meaningful. And so like all of those things need to be met by the project brief. And I would say within each discipline, so like within the discipline of textiles, within the discipline of biology, like the process needs to be innovative. So I think like there are like lots and lots of ideas that can come up, but the ones that I think are really lasting and durational and turn into projects are the ones that like can withstand the interrogation of like, oh, is this interesting within your discipline? And is this interesting because it like checks off enough boxes of like what it means to have integrity as like an Oxman idea? But I do think that like all of us within our fields are like coming up with different ideas, like, oh, could this be like a medical tourniquet, or like a like an orthotic, or like could you do like biomineralization and gene expression, or oh, like what if you could do a some sort of like PCR test on the back on the biopolymer to like trace it in the wild. Like these ideas come up all the time, and then like sometimes they just like go away, or sometimes they come back. Yeah. So I would say it's very organic at Oxman. At a place like Apple, it's like a little more top down, where it's like, you're gonna make an iPhone every year, so the iPhone teams, they know what they're working on.
I have one more question.
Mhm.
Audible.
Mhm.
So, what is something about working with Neri that will surprise every one of us?
Sorry, what was that? Could you repeat the question?
What is something working about Neri that will surprise every one of us?
Mm. I don't know if I caught that in full. I think it might be in audio.
So it
Oh.
what is something that
I really can't. I think the audio is cutting out.
Hello. Is that audible?
Yeah, you're great.
So, yeah. So she was asking that what is something working with Neri that will surprise all of us?
Oh, that will surprise all of you. I can't say that. Let me think. Well, I would say like one thing that I think is actually very surprising. Most people will say this is like Neri is really just like a very, very empathic person. She's just genuinely very, very nice and like so thoughtful and so warm and earnest. And so I think that something that is really great about Oxman is that that warmth, it's just like it suffuses the whole company. And so anyone that comes in, the hiring protocol is like Nara used to say, like brilliant but kind, which is like that person needs to be really, really good at what they do, but they also need to come in with like integrity and spirit and like the spirit of collaboration. I think like so important to any sort of collaborative studio is your ability to like meaningfully work with each other, especially in disciplines that are so different. So I would say that most people who meet Neri, they're like kind of surprised by like just how thoughtful and kind and warm she is. But I do think that that is something that is like it like affects everyone. It affects the company culture, and yeah, like there's like an image of the space which I didn't put in the deck, but like we like Neri really loves dance, and so like there's a picture of like all of us dancing in the space, and so I think maybe that's surprising. It's like more playful than I think it looks on the outside.
That's really nice to hear. We've only seen like documentaries, and today through your presentation, we also got a nice look of the place. That was nice.
Yeah, it all like it looks very like serious and put together, but like sometimes they're very unserious.
I think we will head towards our closing question. So, what is something that you learned from your journey that was really hard that you would like us to take through?
Yeah, I don't know. I think so something that was really tough for me is like developing like very, very deep expertise in something where I think that like sometimes in order to go wide, you need to go deep. And this is just my personal experience. I don't know if other people feel this way. They're like generalists and people sort of like who can do like a lot of different things. I would say that like my experience has been one of like very intense specialization. And there are a lot of parts of it that I would say were like very challenging, is like oftentimes you find yourself doing things that are like outside of your comfort zone. Like for me, coming from a design background, picking up more of the engineering was like truly like it was like a lot of like hardship and like self-learning where especially in an environment that is like mostly engineers, I think you always feel like a little bit that you don't know enough or you're always trying to catch up. So I think that just like trusting in yourself that you're capable of doing things that are outside of what you currently know or what you were sort of like trained in, but to like persist in that, it can be, it's not like you'll have like gratifying results the next day. Like it can be like years in which you're sort of like just struggling with concepts. Like, you know, you might be like trying to do something like statistical analysis and you're like looking at like plots and graphs and it's like completely outside of your knowledge and your wheelhouse, but just to like continue persisting in that, like on the other side of things, you'll find that like you have a really, really robust toolkit for doing what you do super well. But it's like a process. It's like in some ways it's like a many year process and you only really like feel that you are like doing it and doing it well, like yeah, I don't know. Sometimes it's not obvious and it can be like really frustrating. Like you can like yeah, it can feel really hard sometimes, but it's worth it. Like becoming really good at what you do and like developing the expertise and like just doing it unyieldingly.
Thank you so much, Jessy. The session was lovely. We all had a lot to take from it, and it was really nice of you to cover different scopes and areas such that like the audience was able to take something which they're interested in. And there were a lot of new areas that we weren't aware of before, but this was something really nice that we could see how textile is connecting with technology these days and how it's going ahead in future. And there are so many instances that we can go back and think upon.
Yeah, well, I'm always excited by seeing people who are like curious about textiles, curious about design, about making things. So yeah, I'm encouraging all of you just to like go forth and like do exciting things and be excited in the world. I think it's just such a great time. So yeah, thank you for having me.
Thank you.
Thank you.
All right, over and out.
Thank you.
Bye.
Bye-bye.
Thank you so much. Bye-bye.
Oh,